Dr. J
It's
lessons.
It's on the...
I'll show you, actually.
Okay. Click in the description.
All right, I'll show you once we get the screen up here. All right, there's a whole bunch of problems from page 27 that I want to take a look at. So if you got your homework out for page 27, we're going to take a peek at a couple of those. So the plan is simple. We're wrapping up all the pre-calculus stuff this week, and then Monday we're going to start on actual calculus stuff. Okay, there's always got to be that little time to get started to get us going, which means the last homework assignment, which is page 34. Page 34, that's due on Monday. So page 34, that's the last assignment. We're not having a test on the pre-calc stuff. We're just moving right on. We'll just have these little quizzes, though. Okay, so I'll just go in order. So number 4 was f of x is equal to the square root of x plus 3, and we just needed to find these functional values. I think the first 3 were probably fine, but maybe that fourth one kind of threw some people off. So let's make sure that we understand this. So the whole point, this goes back to the function box, okay, where we put something in, and then we get something out. Okay, that's the whole point of the function box. So when I plug it in here, I'm just saying square root of negative 2 plus 3, and that equals the square root of 1, and the square root of 1 is 1, so that's good. Next one is the square root of 9, which is 3. This one here is the square root of negative 2. Okay. Now we live in the real world, okay, and so we won't work at all with the imaginary numbers. Okay. So with this one, in the real world, we'll say that this is undefined because there is no value. Okay. We can't plot a point on that. And this also tells you that negative 5 is not in the domain of the square root of x plus 3 function. Okay? You put something in and nothing comes out. All right, then look at this weird thing. It's f of x plus delta x. Okay? Well, I don't know about you, but what we did each time of these, didn't we take this negative 2 and plug it in for the x, and that's why the negative 2 was there? So wherever there was an x, that's where we put it. So the answer to this one is the square root of x plus delta x plus 3. That's the final answer. Look at what we did. We put the x plus delta x in the spot where the x was. Yeah.
Does x plus delta x be in parentheses, or is that not?
No. For this one, it doesn't matter because it's just adding. Okay, if it was something minus x, then yep. Okay. Now remember, so if I say to you, what's f of alpha plus theta? Okay. Here's my function f. I'm finding what's f of alpha plus theta. Well, that's the square root of alpha plus theta plus 3. Because that's what we're told to do. That's what we do. We take that function, we take that value, stick it in for x, and then just get whatever we get. Okay? I mean, you could put anything in here. What's f of smiley face? Of course, the square root of smiley face plus 3. Okay? You just, this is one thing, this is one time where you just do as you're told. Okay? All the other times you say, why do I have to do it that way? This one here, you just do it. Okay? We'll keep that in mind. So the next one was domain and range on number 18. What is the domain and range of this function? Well, this is called a rational function. A rational function is a function that has a fraction, okay, a numerator and denominator in it, as this. And so the question is, what does this look like? Well, does everybody agree that this is related to the f of x is equal to 1 over x parent graph? Okay, it's related to that. It's in a little shifting going on in some way. Okay, if I take, if I say x minus 1, what does that do to the graph? It shifts it. I can never remember if it's to the right or to the left. You ever have that problem? Okay, I don't know. I see x minus 1, I'm thinking, okay, it's got to go to the left, because negative is always left. Okay, but it's not. This one goes to the right. So what I do is I play the game. Let's make a 0. Okay, let's make a 0 always works. So for example, x minus 1, you say, well, set it equal to 0, x minus 1, and let's find out what the shift is. If you set x minus 1 equal to 0 and you solve for x, you get x equals 1. Not only does it tell you how far to go, but it tells you which direction. The answer is positive 1, so you're going to move in the positive direction. Okay, so this graph right here is going to have not an asymptote at x equals 0, it's going to have an asymptote at x equals 1. Okay, because the game, let's make a 0, tells you where it is. Okay. Now the second one, this has got a 2 on it here. So the 2 just takes the shifts. We know it's going to look like this based upon this guy right here. And the value that it has right here is dependent upon what value we're going to get from the 2. But we just want the domain and the range. So the domain of this, I see that I can plug in every single number and I get a point that comes out of it, except for when I plug in x equals 1. X equals 1 is a no-go. And then if I go past that, I'm good. So the domain is, we can say all real numbers, okay, except x cannot equal 1. Okay, that's the domain. Range is every y value exists as a result of the function except for y equals 0. So the range is all real numbers except y cannot equal 0. Yes?
Would you rather have your notation or with the notation?
Either one is acceptable as long as you do it correctly. For this one, you can say negative infinity to 1, comma, or union symbol, 1 to infinity. Both are correct. Mathematically, any notation that is mathematically correct is okay. You'll see this one more often on the multiple choice than this one. Yeah.
What is like the test consist of? Like, is there any multiple choice and stuff?
Great question. Can we hold off on that just for right now? Or do you want to find out now? Do you want to know? Yeah, we'll get to it. I want to make sure we get through this stuff right here. It's online too. You can look it up. All right, so that's that one. 19 and 25. Oh, by the way, this one right here, you can play the game of let's make a 0 on any function as long as you're shifting. Look at this one. I don't know. The square root of x plus 3. Do I go to the right? Do I go to the left? Just play the game. If you solve this, x plus 3 equal to 0, you set the x plus 3, that part right there. You solve it, you get x equals negative 3. That tells you guaranteed I'm going to go 3, I move over 3, and I move to the left. And so therefore, this one here, 1, 2, 3, starts here, just like that. Works every time. You don't have to worry about horizontal shift, left, right. Well, there it is, right there. Okay. Let's look at 25. My light person. Here we go. Hit them all. Now, I want you to know I tried this, and it didn't seem to work very good. So, I don't know if anybody saw that. So, I'm going to try this. I have no idea if this is going to work, but you'll have to zoom in. It's something to do with the lighting. All right, so this is number 25. It's a piecewise function, f of x equal to 2x plus 1 when x is less than 0, and then y equals 2x plus 2 when x is greater than 0. So they're both lines, except you see what happens here. This is 2x plus 1 when x is less than 0, and then 2x plus 2 when x is greater than or equal to 0. Okay? They don't connect, right? Which is fine. Nothing wrong with that. The only thing that Desmos doesn't have, and your calculator is really bad at, but your kids' calculators will have this. Guarantee it. Is that this one gets the solid dot, and this one gets the open dot. Okay? That's the connection that you have to see. This is important that you understand how piecewise functions work, because we're going to end up doing a lot of stuff like that. Yes?
How do you know Desmos?
Yeah, I had to look it up. The way it goes is, I don't know if you can see this. First you state the domain. So you got to put a curly brace, a left curly brace, then x is less than 0, then a colon, and then 2x plus 1 is the graph. So you give a combination of, you tell it what the domain is, and you tell it what the function is, and then it will graph it.
Okay.
You can even look up, I Googled it, Desmos Piecewise band. There it was. Okay. Now, I want to show you something else as maybe a hint. Number 19, you were asked to graph this thing. And so number 19 was the square root of x plus the square root of 1 minus x. Okay? How the heck do you graph something like that? Well, let me teach you something that maybe you know, maybe you don't know, I don't know. So this is the graph of the square root of x. Piece of cake. Okay? This is the graph of the square root of 1 minus x. Okay? If I put them both on the same thing, this is what it looks like. So you can see from here that the domain is a combination of both pieces. Okay? If I can't use it in one, then I can't use it in the total. So this means the only place that these guys overlap is between 0 and 1. Okay? So the addition of those two is the purple one. Okay? Now, I'm going to try to enlighten you on something here. So what I did was f of x is equal to the square root of x. G of x is equal to the square root of 1 minus x. And then h of x is equal to f of x plus g of x. I just add them up. And you can do this on your own calculator too. Okay, but this is I'm just using here. Now watch this. A summation function, a function that has got things added or subtracted to them, is actually each of these values individually added up. Okay? So what do I mean by that? Well, look at follow my colors here. So this is, I'm going to do x equals 0. X equals 0, on the blue function, the answer is 0. X equals 0 on the green function is 1. 1 plus 0 is 1. So on the purple graph, I plot a 1. Then watch this. For each of the values, I'm going to add this value, this y-coordinate, plus this y-coordinate, and I get this as my answer. Because that's what I'm told to do. I'm supposed to take f of x and add it to g of x. So take the y-coordinate from one, take the y-coordinate from the other, and add them up. See what I'm doing here? And then the last one is this one. They're both the same, so the answer to it is double that. So anytime you see a function that's like a combination of other functions, this is all it's doing. Okay? And then that's how we come all the way back to here. This one plus the 1 gives you that. And that's where the whole thing comes from. It's actually kind of funny if you look at something like this. Watch this. Take a polynomial. Take a polynomial, any polynomial. So I'll just say b of x is equal to x squared. Oops. And I'm going to get rid of these guys. So there's b of x, and I'm going to say c of x is equal to 3x. And then d of x is equal to 1. Okay? Now watch this. If I say e of x is equal to b of x plus c of x plus d of x. And e, did I already use e somewhere? E, F, G, H, I, J, Q. Okay. Q of x is this one right here. Okay. Now, watch this. I'm going to get rid of this. This is a parabola, which is x squared plus 3x plus 1. But most of you have probably never viewed it as the x squared value plus the 3x value plus the 1 value for every single x. So watch this. So here's the x squared, here's the 3x, and here's the 1. So let's just pick out a value and see if we can get one to work. How do we get where it's the red one that we want. Let's try to get 1, 2, 3. I can get this one right there. Okay? Where does this come from? Where does that dot on a red graph come from? Well, the x squared is the purple one, so it's going to take this coordinate. Okay? It's going to take this length, and then we're going to add to it the yellow one, which is this length. Okay? We take those two, add them up, and then we add it to the black one, which is right here. And if you take those three, add them up, you land on the red one, which is actually from where I drew it, about right there. Did you see what I'm trying to get at? Okay, that a function which is a sum of other functions is really the addition of each of the values for every x. Add each of the y's. I don't know. Sometimes this can help you to graph something goofy that you've never seen before, and you're out to figure it out. Make sense? Okay. All right. Backboard. So 46. The question is y a function of x? Okay, thank you, Bitsy. Come with me. Stare at Libby. Yeah, all right. Okay, so what does it mean for y to be a function of x? Okay, y as a function of x is a situation where if you plug in x values, you get only one y value. Okay, so what this means, the quick way to do it is if we could somehow rewrite this so we could solve it for y, then we'd have that y is a function of x. So I'm going to see if I can solve this thing for y. So let's see, x squared y. I'm going to throw this guy over on the other side, so it's plus 4y is equal to x squared. Watch my math here. Then I'm going to factor out a y. So I got x squared plus 4. I got that. And then I can divide. Y is equal to x squared over x squared plus 4. I was able to solve this function for y, which means that y is a function of x. If you can type it in your calculator in function mode, then y is a function of x. So it's as opposed to x squared plus y squared equals 25. Is y a function of x here? And the answer is no. Why? Because when you solve for y, you end up with a positive and a negative value. Okay, function. So the simple way to put it is, you get y squared is equal to 25 minus x squared. At this moment, you know that y is not a function of x because y has an even power. Okay? You can't type this in your calculator when you're in function mode because it's built into your calculator, isn't it? Y equals. Okay? That signifies a function. What's that? Yeah, let's try that. So if we say, well, let's just take the square root of both sides, then we get y is equal to, but what I have to do is I have to take into account both the positive and the negative. So what we've done is we've split this now into two functions, not one. And if you can write it as one function, then y is a function of x. Does that make sense? We can simulate this circle by drawing both of those, but we can't simulate it using one function. What was there, some kind of test for a vertical line test? Yeah, that's right. All you had to do is just like draw the line, right? Fails the vertical line test. Why? What's the deal with that? Why does that work? What's the point of that? How does it know? 1 point? This would have 2 points. Okay, so why does that work? What is the point of that? Like what? How does that prove that it's not a function? For one input, you're getting two outputs. Exactly. Imagine that magic function box that I got there. Imagine me putting a 3 in, and then I get like a 7 out. And then I put the 3 in again, and then I get a 10 out. The only way that can happen is if it's not a function. Because it's legal for that to happen, but it can't be, it's not a function then. So if something's not a function, what is it? Do we have a name for that? We should have a name for it. It's somehow there's a relationship between the input and the output. There's some sort of relationship for it. I suppose, let's call it a relation. It seems like a good word. A relation is a name for something that has a correspondence between an x and a y, but it's not a function. So x squared plus y squared equals 25 is a relation. It's not a function. Okay. All right. Number 64 was the ripple question. You throw a stone into a pond, and the ripples appear. Okay. So if you study this a little further, which they did, they said, hey, here's the deal. There's actually a function for the radius at any given time. So you plop a stone in the pond, and then you watch it grow. I did that this summer, by the way. I was in a lake, threw something in there, I just watched it. Calculating the radius, the rate that it was going. And then I woke up. No. So what this is saying here is that the radius is dependent on the time. So the time, as time ticks by, this might be like 1 second, 2 seconds, 3 seconds, 4 seconds. Okay, you can figure out what the radius is at any given moment based upon the time, because it's a function. And then they said, well, wait a second. The area of a circle we know is pi r squared. Okay, so that's another function that we know. Then we have this thing called a composite function. So what would what would a of r of t mean? That's a composite function, one function inside of another function. What on earth would a of r of t mean if the r of t was the length of the radius at any given time, and the a of r was the function which was the area of the circle at any given radius? Kayla.
Plug in R for A then?
Sure, so let's do that. Plug in a for r. I'm not sure if,
For R
yeah, plug in r in for the a function. So I'm going to say this r, yeah, r of t, right, is going to go in for the r. So it's going to be pi times 0.6 t squared, and for good measure, I'll write this as a of t. Look carefully. R of t is equal to 0.6 t. A of r is equal to pi r squared. So a function in a function, I put the r function into the a function. You got to see how it fits. See how it fits? Okay. So last year, remember this, doing f of g of x, g of f of x, blah, blah, blah. Okay, so this is a composite function with a practicality here. What does this tell you? What does this function here do? Tell you? Kayla? Area at a given time. Very good. It says, hey, for any one of those times, if you punch it to this in, it'll give you the area of the circle at that moment. You see it? Because it's the area based upon the time, not the area based upon the radius. It's the area based upon the radius, which is based upon the time. And they're all put together into one. Okay. We're going to work a lot with composite functions in this year too. Okay, the whole even versus odd thing. So even versus odd. What does it mean to be even again? Symmetry over... Were you saying something smart, Alec?
No.
Oh. All right, so what does it mean to be even? Both sides. What sides?
Both left and right have the same.
Left and right.
That's understandable.
What if I'm in space?
If you're in space, then do your left and right.
Okay, I'll help by clarifying here. What does it mean to be even? Symmetry over the y-axis. Okay. So, how does that work? Well, if I have some function, I'm going to make up some function here that is symmetrical over the y-axis. Okay. Would we say that that function is even? Yes. If I call this f, then watch what's happening here. If I plug in a random x value, then what I get is an f of x value. Right? Plug in x, I get f of x. But if it's true, if it's an even function, what happens here is if I plug in negative x, it's also equal to f of x. So somewhere in your book it says something like functions that are even, what happens here is f of x is equal to f of negative x. And that's what that means. That's the picture that goes with it. Good? Okay. Odd functions, what's with that? Symmetry over the origin or through the origin. So we have y equals x cubed is a function that is odd. So if I say this is the function f, if I plug in an x, I get myself an f of x as an answer. That's the y value. It's the height of the function at that moment. But if I plug in the opposite of it, because it's symmetrical, I actually get the opposite of the f of x. So according to your book, they said some fancy rule that f of x is equal to the opposite of f of negative x. F of x is equal to the opposite of f of negative x. Okay? And so that's what that means. You guys are all raring to go today. Yes, ma'am.
Yeah, because then the other part is flip it down. The idea is that f of x is equal to the complete opposite of f of x.
Is this what you want me to say?
Yeah.
Okay. So we got to argue the case. Is f of x equal to the opposite of f of x? Say that again. That would be symmetry over the x-axis. So a picture of this, if I have a function, which is not a function, it's a relation, and I plug in x, this gives me f of x, okay? This would be the opposite. Here, f of x is equal to the opposite of f of x. F of x is equal to the opposite of f of x. Yeah. So we gotta make an agreement here. What does this mean? Well, this says if I take the opposite of x, which is this guy over here, and I plug it in, what I get is the opposite if I plug in the x value, not the negative. Plug in the negative, I get the opposite of the regular x. Yeah, Connor. Leave this one out?
No.
Okay, leave that one in. Leave that one out.
And then put the f in parentheses.
And you did this?
Yeah.
Oops.
That makes sense.
I'm going to delete that off the video. I'm not even going to touch it. Okay. You ever make the smudge worse by trying to do it? Okay. What?
Oh, it's on the wall.
I know it's on the wall. Oh, now it dried.
Don't you have the expo eraser?
Now it's smudged.
No, smudged it on the wall so it's black.
We're all everyone on the side.
I know. I'm all warm right now.
I'll show Chamberlain.
All right. Does this fix it?
That makes sense to me what she would say.
Oh,
That the entire thing is negative, like it's the exact opposite.
it's the exact opposite. We have to somehow say that the values here are then the opposite of the values here. And that's what we're trying to convey here, I think. But this, mathematically, that f of x is equal to the opposite of f of x.
We distributed -1.
Yeah. I can't go along with this.
It just means the opposite, and it is the
Because
exact opposite.
the negative on the x is telling you to go to the negative side of the x-axis. And the other one's telling you to flip opposite on the y.
Right.
So you need both.
Yeah.
Right.
I can.
We got to do both.
Because I feel like that one's just saying like that graph or down.
Yeah. Right. It is saying exactly that. Another way to say it. If you pick a value other than x, so if I said, oh, give me an a, then you're going to get f of a. Okay. But if you plug in negative a, right here, you're going to get the opposite of f of a. This is good for us right now, because what's happening here is you're trying to make sense of a complex statement written mathematically, and this is the essence. Normally, if you just skip this stuff because it gets a little hard, that's the bad thing. That's bad to do. Okay. Okay. It's like doing the whole worksheet, and then you got that one with all those words in it, and you say, well, I'm just going to skip that one. Okay? No one here has ever done that, right? Okay? That's the good stuff. That's what we're going to focus on. Okay? That's what we're going to focus on. So we're going to work towards always trying to make sense of the hard stuff, because anybody can do the easy stuff. Remember, you guys are the smart and talented ones that I want to have be different than everybody else. Okay, hey, I wrote this on the board yesterday and we didn't get a chance to fix it. Okay. Gunnar was going to say something right at the end.
I was going to let somebody else figure it out.
Okay.
Time, though.
Yes.
So like you can't cancel the a minus b because a minus b is 0 and you can't divide by 0.
You cannot divide by 0. A minus b, or a is equal to b. Okay. She's saying, watch this, if I subtract the b from both sides, does it make sense that a minus b is equal to 0? Because they're both equal. When you divide, what I didn't draw here was this step right here. I just canceled. And this division by a minus b is 0. And that's the flaw that disproves that says that it's actually not true.
Next time.
Next time.